like a first step. Again, I'm just a PhD student at TU Darmstadt, working with, I guess, multiple groups on, like Gregor just said, like maybe meshless methods. Also, I did a little bit of load balancing on CFD meshes. So it's like related to, in general, to OpenFOAM more than anything else. And today we are here to just, like Gregor just said, also just to give my opinion on a little bit on what programming paradigms are currently used in C++ CFD field, at least the open source software part. Uh, but then we can discuss a little bit on what improvements could we make, and what things to keep basically for any kind of next generation CFD package you would be interested to write. So first of all, I will go through quickly just about a little bit of programming paradigms, what they are, and the most common ones. And next, I will go through the most important principles behind them, and why people just chose these approaches for CFD. And next, we will actually go through uh, quite a large list of design patterns, but of course, it will not be all of them. It's just the ones that I deem kind of important or common enough to mention here. Again, in kind of the CFD niche or type of software. And as last thing to do is just to go to go through a couple of interesting applications of different design patterns, and how they like play their roles into the bigger pictures, which is kind of the programming paradigms that CFD developers chose for their like for driving the development of their software over the years. So yeah, the first thing I want to start is just, in my opinion, programming paradigms are always connecting to how do you manage state in your software, right? So basically, it's very hard to imagine a CFD software without the state. Because you will need some kind of mesh, you will need some kind of fields, these types of things. So the first one is the procedural programming approach, which is, I guess, it's the most simple one, and it's probably everyone knows what it is. It's just uh, like take a state and you mutate it externally to code. So you write a function that just mutates everything. So it has access to basically everything. You feel like all of your variables are kind of global in this sense. And of course, one good thing about this kind of approach, which you will see a lot in maybe C code or old-ish Fortran code, which you just see functions taking references and just returning void. So they must do something to those references. And the nice thing about this kind of approach is the algorithms are really clear and simple. You get a list of instructions converted basically to functions, and reading the code is very easy. But the biggest problem with this approach is once you give people multiple ways to mutate your state, well, bugs will appear. Basically, that's it. And debugging just becomes way harder because in this very simple example here, we have an x that we increment, and someone else might write a function, another function that takes the same x and does something else to it. And then at the end, when we get an unexpected x value, it will be very challenging to just guess where the error might be, you will have to go through that list of debugging functions and so on. Well, of course it gets a bit easier with debuggers, but still it's not a hygienic way to go about things, at least not in like fully fledged CFD software. Right, so to kind of mitigate this problem, of course, object-oriented design came up, which basically couples the state with the behavior that changes that state. So our counter now is just a class, so it is a kind of an object that holds its state internally and has all the, let's say, the functions that can access it uh, as an kind of an interface to that object. I mean, when it comes to object-oriented design, I think it's pretty common. I guess most people know about it. You kind of hear about like 3 to 4 things. Is that there is inheritance, which, by the way, means just you have a counter class here. You can like write another counter class that does the incrementing differently. This, in this example, might be a little bit dumb to do, but still it illustrates the point. The next concept is maybe polymorphism, and it's when like different class types have like basically the same interface. You have something like random access lists. You have like that indexing operators and so on. So you will know that all types of lists, like a list or a vector or tensor or something like that, will have some kind of accessing operators in that indexing sense. Of course, if they are like random access containers. Right. The next two, it's like maybe encapsulation, which I just said. It just helps maybe manage your state in a more like organic way, in the sense that that if in this example here we have X as like a private member, so you know for a fact that not all like external code can modify that X. So if there is a problem with that X, it's probably in this class, or maybe if it's protected in one of the children, like child classes. Yeah, these are the most common like concepts around object orientation, and it just really makes sense to make a lot of things objects. So in CFD, you would have a mesh like as an object. You would have a field as an object, like on the mesh, like a pressure field, temperature, velocity, something like that. Right. So I just wanted to mention Tomislav's talk about object-oriented design in OpenFOAM in particular. He goes into a little bit of like detail in there that I'm not really ready to do right here and right now. Of course, we will go a little bit into more detail as we go, but if you're interested, just check that video of his. I will share the slides later, so you will have access to everything else. Well, the problem is not really fully resolved though. So you still have a state and you have some code that alters that state, and that's when like functional programming comes in. And when what these guys do is just to eliminate all state. So you would have a full program without any states whatsoever. So nothing gets like mutated in any way. And the most common, languages for this kind of paradigm, at least the ones I know about, are maybe Haskell and F Sharp. F Sharp is like a .NET thing, so it's a Microsoft thing. But again, there's not really so many like scientific computing frameworks there. Well, it's the linear algebra that they are really lacking. So it would be very challenging to implement anything in those languages, at least to get the same efficiency level as to choose something like C++. All right, so the most common symptoms of these of this type of paradigm is the pure functions, which are basically functions that have no side effects. So they use nothing like out of their scope, basically, and they change nothing out of their scope. So in an exemplary manner, you have here at line 3. Here you have a C++ lambda function that only like passes things by value and has no captures, basically, and just returns like a value too. So this increment function here is what we basically call a pure function in functional programming. And the reason they enforce this type of approach here is so they cannot write something that does not make sense really mathematically. So you wouldn't be able to write x equals x plus 1, because this, from a mathematical point of view, this equation has no no solution, basically. So it's just flat out wrong. So they don't like this. So what they do is everything is basically immutable, and every time you call up your function, you get just a new version of your whatever variable return type you have. Basically, it's still really it's compared to object orientation is still a new paradigm, but it's kind of fast growing, to be honest. But I really see it a little bit far to adopt something like this for CFD software. And basically, it's the most basic example is just a for loop is no longer possible in functional programming languages, for the simple reason of not being able to increment that index, so the I index that you need to increment to go through something's element. It's just what you will not be able to. Of course, they have like a little bit of different approaches with a little bit of recursion and maybe mapping, some stuff like that. But again, it's just with linear algebra frameworks, it's really lacking there. So they don't really have much frameworks you can work with, basically. From there, we get to like a little bit of I would say out of context programming paradigm for like CFD software, which is the declarative approach, which basically not really dealing with the state as much. It's more about like queries. So say you have like a database system, and I'm not sure if everyone is familiar here with something like SQL or this, where there's no actual like really traditional programming. It's all about queries and rules and stuff like that. And you can see this also in the those logic programming languages, basically the ones that you use to prove theorems and whatnot. So these are not really traditional programming languages. They're just there for the declarative approaches. And you can also do this in C++, basically, but it's kind of a little bit of a new thing here, where we basically have the pure function version of the incrementing function, and we have some kind of state. So it's like a vector, and you say, here's my state, and you transform it in a way. You don't really care how technically like the transform is carried out, as long as it increments the vector values. All right, so you will get like a result back with incremented values anyway, and that's what it is about, basically. Now this views here transform can do things. Where is it? Can do things on its own like way. Basically, we don't really care if it's lazy evaluated, if it's not lazy, if it uses template expressions, anything else. We don't care about like the much details, and that's what declarative programming is. So basically, when you see something like an HTML file, or all of the web stuff mostly, and the database systems, and of course your CFD code can interface to those code bases too. So it's nice to just be aware of what they are doing there. The next one, which is a little bit more like important to in CFD context, is the parallel programming one, which just means your state now is shared between multiple processing units, and you really have to take care of how you manage this state, because just accessing that state or writing to it at different times can get you into like race conditions or deadlocks or whatnot. So multiple kind of techniques have emerged to combat this with in the at least C++ standard library you will find locks, mutexes, uh, and you will try to like use atomic operations as much as you can, if you know that you will do some multi-threading in your code. So basically, the newest thing I've heard about here is like in terms of C++, is they have added like an execution policy. I think since C++ 17. I'm not even sure if you need like maybe an NVIDIA compiler to make this work, but the basic idea is when you have a state, at least the C++ algorithms always have an execution kind of policy as a first argument now, which you can pass in, which is really like a shame, because most of OpenFOAM has been developed pre, like, let's say, a standard library, and it's not really used that often. So I hope this will change with time. So instead of your own loops, you can just call transform with an execution like parallel policy, and it will take all of the data and share it properly across your, whatever you have, like CPUs, GPUs, other accelerators. I guess it has like a wide coverage of hardware to use there. If you're interested, like specifically in knowing more about how MPI is kind of used in OpenFOAM, there is a workshop I do like regularly, also as part of like NHR training, and there is a link to the website to the website there. Right. And the last programming paradigm I want to mention here is the generic programming kind of approach, which in C++ just means templates. We don't really. It's more like you forward state management to another paradigm, but you make your code kind of your behavior code kind of type agnostic in most cases. Well, it's probably more technically correct to say it's type aware, but agnostic is also kind of fine for most cases. So what we have here in this example is like a concept for something that you can increment, and basically saying it needs to be move constructible, and it needs to accept kind of this syntax that says x plus 1 if you have an x of type t here. And that will need to be convertible to T2. So whatever you have here. So this concept kind of separates what you can use and what you cannot use with this increment function here. Well, template function, to be honest. And you can see here, instead of the type name or class, you will have the concept name there, which is incrementable in this case. You don't have to really worry about this because you will probably have an STD like incrementable like concept in the STD library, but still it's just to illustrate how things can get really complicated very quickly when you do generic programming on another kind of type of paradigm, which in this case here is kind of functional programming. Uh, well, half. So because here we do kind of change the state. But typically you will say that anything that works with +1 and is move constructible, you can run that increment function on, which is very generic in itself. So you don't really care about the actual type. You just care about its interface, that it has a move constructor and it has maybe an operator plus to an int, basically, all right? So, and the move constructor I just required always is just when you return a value in C++, like recent compilers will invoke the move constructor instead of the copy one, because this typically is a copy. If t is not a reference, basically. So these are like the most common ones, and as you can see, it's very hard to just stick to a single one like type of programming paradigm through your whole code. So within any kind of code base, you will find a lot of examples from different programming paradigms, but there should be like just one dominating everything, and that's it's just to make convention easier to grasp. So let's just jump right in, and I will kind of breeze through these principles because are kind of easy to understand. So the first thing is uh, it's just good to program for your interfaces. So by interface I just mean like in an object orientation kind of setup. By interface I just mean public functions, to the classes. These are your interfaces, and maybe well, I mean in C++ context, it's in other languages it's a technical term too. And you have some kind of maybe free functions that are accessible everywhere. So these are your interfaces, basically. All right. So the first thing I want to mention is how important it is to make your API stable and easy to work with. Right. So again, the API is your interface. So it's like the public functions. It's the public interface, to be uh, precise. It's you have, for example, let me actually show you this kind of a little bit of a small project we worked on as the OpenFOAM data committee here. That we needed something to connect like a database system to OpenFOAM, and we kind of for some machine learning and AI stuff. So we had this kind of smart Redis here. It's like a wrapper around the Redis database to work more easily on HPC. So once you start a project like this, and I did like a little bit of a client adapter thing to smart Redis API. What I want to bring your attention is, let me see if I can make it a little bit bigger here. It's that the interface is basically split into three layers, right? So there is what I call the service API. This is used just if you don't really care about anything at all. You just want to send some fields from OpenFOAM to the database or get them. The interface should be very simple here, and of course it's like constrained a little bit by the Redis interface too. But again, you just invoke send geometric fields. You give it a list of fields of any type, and it just does all the things for you. So this is kind of the main entry point to the library, right? And then you can provide multiple levels of access. So it's if you need a little bit more control, you would maybe pass a data set, and this is like a smart Redis thing, which we pack the fields into that data set, and then you can do whatever you want with the data set and send it out, your own ledger, let's say. And the third layer is just a fallback layer that just sends an OpenFOAM list, like a named OpenFOAM list on the database. And of course, there's like getters and equivalent getters to to receive the same things again once you've done some ML stuff on them. Right, and then, like I said just now, if you just stick with open, like with object-oriented design, the interfaces are really focused in there. So you should be just fine, and you can also enhance it more with generic programming, just like we just saw it with this X+1 example. So any type that has an interface that will support X+1 will work for this code here. And if it doesn't work, and by the way, if const expression is like a compile time thing, so if this condition is true, so, this code gets compiled. If it's not, the other code gets compiled. So there is no like runtime overhead or this type of things here. It's like all meta programming. It's all at compile time. Right. So once you get your kind of interfaces done, the next point is to kind of separate your concerns. So by concerns is like a technical term. So basically, if you put everything in one class, then you will get into trouble like in 1 week. But if you separate your concerns into multiple objects and multiple classes, that need only to change like for only one reason or maybe two if you are permissible, but then like I said, so in a CFD like context, you have a boundary condition, you have a mesh, you have a field. So these concerns, you should just separate them into different code structures, let's say. Whatever you are using, if you are using functions, so be it. You are using classes, same thing. So what this and OpenFOAM does this like marvelously well, and it takes it like one step forward by making like almost everything as a dynamic library. And you can load it at runtime. So you can program your own stuff and just load them at runtime. And we will take a look quickly at this kind of particular example here, where you can register things and just load them and work with them without actually altering the OpenFOAM code base. All right. So a very simple example here that I also recently worked on is a library called Blast IMR, which does load balancing for adaptive mesh refinement on polyhedral meshes in OpenFOAM. So even if this functionality is not really existent in OpenFOAM itself, you can still hook into the dynamic mesh class and make your own dynamic mesh, and it just plays well with everything else due to that like registering systems and that separation of concern kind of principle, which by the way allows for parallel development. So if you have like something everything shoved into one like structure, well, not many people will work on that, let's just say that. Right. This one is kind of a little bit personalized opinion more than anything else, but it's almost always composition is better than inheritance, but of course composition has a little bit of an overhead, like a runtime overhead, because of the what you call maybe indirection, more indirection levels. So it's very hard to find an example in OpenFOAM that does composition like in an organic way, because it's kind of well, OpenFOAM is inheritance based, so it's like very, very strong on the object orientation. But if you take a look at, for example, SU2 here, uh, I'm not sure if you have heard about this before, but it's also like an open source CFD project, a little bit. And you can see this is like a model for a fluid, some sort of fluid, and you can see the viscosity, the thermal conductivity, the mass diffusivity are all like parts of the fluid model class, instead of the fluid model class inheriting from these. Right, and it just makes it easier in the long run because of something called the weak base class problem. So because if someone changes the base class and you don't really control that base class, it becomes like a maintenance task to always be up to date. For example, here in my framework that I just mentioned, Blast AMR, I'm always on the lookout on changes for the dynamic mesh class in OpenFOAM because I don't control that code, and I will not know what kind of changes that they will have that may or may not, break my code at any point. So that sense of insecurity, you just, I guess, lessen it a little bit with if you rely more on composition in respect to doing a lot of inheritance. Well, and the last principle, maybe I'm little bit, uh, it's too personal, but I do remember the first time I got into this OpenFOAM kind of programming, and I was a little bit impressed at times and angry sometimes at what you can see there. So the first thing is, well, uh, you should strive to make your API really intuitive, and there should be no surprises for the developers that use your API, right? So the first kind of example here is how OpenFOAM represents like matrices. These are like normal transport kind of equations turned into matrices. And even if you are not really well versed into OpenFOAM, you can really just, by reading this line, you can understand what the equation is. It's just a time derivative, a divergence term, and a diffusion term. So, you can make out the terms very, very easily, which is how it should be, right? But there is a little bit of problems, especially with the max and min functions here. So say we have a and b just integers and like an open form field called c. So max a and b will give you whichever bigger, a or b, like bigger in the sense of just comparison between a and b, right? C dot max of C all do the same thing. But there is also G max, which is which was at least for me very, very vexing to see at first, because when I type C dot max, I would expect really to get the maximum value of that field, right? But it's really not that easy. So C dot max will give you the maximum value of the local field in an MPI kind of parallel run. C dot max will only represent the local maximum, which was a little bit of an issue. You needed to use Gmax for like global max to get the actual global max. But again, these are kind of a little bit of design decisions that were made at some point. Someone needed to make this decision, and both decisions will fire back at some point, right? But the really like frustrating one was the c dot max, and then you put something in there. So by the way, these are all maybe like overloaded versions of the same method. but then what would you expect from c.max and then with an argument is to maybe bound the field like maximally, but it does not. It bounds it like minimally. So the minimal like value of c will be 1. So it does a maximum of whatever was in that cell and 1. Right. So these kind of surprises are really so it should be just you should make it like more clear. It's just so c dot maybe bounded something, and it really just makes the learning curve way easier, and also just please avoid the usage of free functions, especially in C++, because typically when I have a C dot, my IDE gets me a list of functions or methods I can use, the public ones at least, and you cannot just expect someone to magically know that there is a Gmax in OpenFOAM, right? So especially if the library is quite large and they have like 3 months to do a master thesis or something like this. All right. So this is like the gist of principles behind those kind of programming paradigms, and I think I'm losing a little bit on time here, so I hope it's fine, Gregor, if we go a little bit of time, right?
Yeah, that's
Okay, cool.
okay.
So yeah, I will try to breeze through this because well, some are more important than the others, but the presentation is always there, and you can check it. I will share a link at the end, hopefully. So uh, when it comes to design patterns, it just means some technical ways to solve a particular issue uh, that is commonly encountered in kind of software engineering in general. So it's not just with CFD or C++ or things like that, but it quickly becomes really, really relevant to the field you are like writing software for, and the programming language you are kind of relying on. Right. So the first category here, and we have like 3 categories basically, is the creational category, which means just ways to help you create objects or whatever things you want to create. All right, so the first design pattern, and I think it's the most widely used, is the builder pattern, and you have multiple versions of this one. Well, the thing is, you want to uh, construct very, very complex objects, uh, but you don't really want to construct them at, like in one go. You will want some steps to it. Well, the very simplistic kind of example for this is when you do an inheritance tree, the constructors will get called like from the top to the very bottom. But this problem the language kind of solves this problem for you, so you don't have to kind of really worry about it. But you still have to call the constructors in your child constructors, but uh, this is carried out by it's like enforced by the language, so it's not something you do. And I have like a very simple example here where if you do like reactive CFD simulations, you probably have a cloud somewhere which has some parcels or particles, whatever you want to call them, like. Uh, and the problem comes when, well, you are doing reactive simulations, so you have to track those particles as they go like through the domain. And the problem is when you have like a parallel simulation where your domain is decomposed and split between multiple, uh, you know, um, uh, processing units, and then one particle moves over to the mesh from the other processing unit, and now you have to kind of take care of this behavior. So and one problem with this is that that parcel will probably most always have some kind of constant reference or a reference to something. So in this case, in OpenFOAM, it maybe has a reference to the mesh object. And the problem is you cannot send something, that has a local reference to another process. That process can be on like a different machine entirely, or running on a different operating system altogether. So what we do is basically send, let's say, a prototype of a parcel, and on the other end, on the receiving processing unit, we constructed step by step, a little bit like, well, it's only 2 steps, but you get the data, all the other data that are not related to the reference, but you use your own reference, like the new mesh reference, the new local reference on the new processing unit. And that's how it kind of works, by the way, these schematics here are just like, maybe they are not like 100% accurate to OpenFOAM code, but they are just there to make sense of things. So when you have a list of parcels, that list, if you want to build it like step by step, you can always just send like prototype data through the input stream, and get to build it at the new location, whatever that is. It's a new process or whatever, with the new mesh, basically. That's the gist of the design pattern here. And there is another one which is very, very similar, but takes care of like a different problem, which is basically when you want to create like a lot. It's like you will still need some kind of generic type systems, but you at the end you will need to create a concrete object. But say we have like an abstract class that is for viscosity models, right? And you have a concrete class that extends that base class, basically for like a very specific viscosity model, is just maybe a constant viscosity or something like this, right? Well, the issue is you don't want to include that concrete new model into your code. Like, you don't want to include the header itself to be able to create, to use that constructor, so to use that class. Instead, what we do is just have the base class create the concrete model for us, and we get back from that base abstract base class a pointer to the new model or the viscosity model that we just created. All right, and because of inheritance, if you have like a virtual interface, for example, correct here is like pure or an abstract class, or it's just a pure virtual class. You can override it in child classes, and then these get executed instead of your top level class, and you get away with only kind of including the header of the base class, because we kind of erase the need for the child type basically in your code. We'll take a look at these kind of examples very quickly. So the third one is kind of the prototype design pattern, which I just explained with the parcels and how they are constructed. So basically, when you want like to have some kind of moving something from a process to process, you will probably want to destroy the parcel on this process and create a new one with new data on there. And that's what a prototyping is. It's just you clone this, remove it from this process, and send the clone over, which is the prototype, which is not, let's say it's an incomplete object, basically, in maybe serialized form. So whatever the serialization is maybe for you, it's like maybe JSON files, maybe YAML files. In OpenFOAM is an input stream, output stream thing. Maybe it's just you write to disk and read again, these type of things. So the last thing from the creational kind of category is a singleton, which is it's a way to enforce the existence of exactly one instance of your object, which is to be honest, I did not really find like a very nice example for this because it's kind of hard to look for. Like in the code, there's no way you can like find it in the code, but there are symptoms that are very obvious. So whenever you have something like all the constructors of the class are private or protected, which means they cannot be used outside of the class, and typically you get like a static method called new or something to just create an object for you and return a pointer to that object. And again, that new function will actually check the state, the internal state of your object. If it's already allocated, it will just return a pointer to it. If it's not, it will allocate a new one. So this is kind of like, to be honest, it's for us, when we did the OpenFOAM smart Redis stuff with the ML and AI interface, we had like, imagine that you are spawning a lot of function objects, but the connection to the database does not really need to be duplicated. The connection to the database really needs to just stay one connection that every object function uses. So this pattern here solves that issue for us. So it's basically hide the constructors and create a new function to just check the pointer state and act accordingly. Typically in CFD context, you will see something like the time class to be something like a singleton in principle, but in OpenFOAM it's not really a technical singleton though. It's just I wanted to make sure that I relay the feeling of a singleton by just saying that there is only one time in most of the cases, obviously. Well, the second kind of category here is the structural category, which is composed of a few different kind of design patterns itself. So there is like the concept of a proxy here, which basically delegates the actual work to other classes, but it helps you manage a lot of maybe types. Well, not really C++ types, but concern types in the same way, basically. So here on the left here we have the FVMesh subset proxy. And it has this interpolate function here. And basically what this proxy does is it can accept like a full mesh, it can accept like a cell set, can accept a cell zone, and still does the interpolation the same way on all of these kind of types, literally, right? So that is what a proxy is. It's a little bit more preferable to inheritance instead of inheriting from the mesh and the cell zone and the cell set and say, oh, this object is everything. Having a proxy is much cleaner. Well, the next one, which is a little bit also related to proxying, but it's more about adapting interfaces to each other. And we kind of needed this when we wanted to do like a coupled CFD and molecular dynamics simulations. So we have OpenFOAM on one side, lamps, I think, on the other side, and you want to make them like talk to each other. with like a nice interface here with that socket form and socket lamps, and the driving code, of course, which is I call here CPL. I did not include a link, but you can just Google CPL OpenFOAM and you can find the repository for that. It was not our work, but I had to actually port it to different OpenFOAM versions. So that's what the experience comes from. Another very prominent example is the precise library in OpenFOAM, which kind of provides adapters to virtually a lot of other CFD or a lot of other software, let's say. All right. The next structural design pattern is called facade, which is kind of it just relies on giving your clients or whoever works on your code an interface, like a simplified interface to either to your libraries or to your large classes. And this is very similar to what I just mentioned earlier about that send geometric fields, that you just pass it like a word list, a list of field names, and it just does the work for you, right? But always, if there is a need to like a little bit more control, you can always provide layered interfaces over that, single entry point to your classes. Right. And at the end of structural design here is the composite design, which is a little bit, more on the composition side on rather than the inheritance. So, for example, you have like a poly mesh. So this is like I would say the base class for OpenFOAM's mesh, which has basically a lot of things, but I just here mentioned the points and the faces, which are two different types, and you have an area kind of method. So these types here, they are lists, and every list is composed of like different objects. So when you call like the area thing, it just gets propagated through the the composition tree, so to speak, and then you get like the data back reduced back to like one singular scalar there. So this kind of design just helps keeping things organized enough, but I really do not recommend going like into many nesting levels, either with composite design or with inheritance. It's just too many nesting is always not a good thing to do. Well, the last kind of design pattern category here is all about behavior of your code, so how it behaves basically. The first thing I want to mention is the iterator, which is very common. With range loops in OpenFOAM, you need like some iterator support. Well, in OpenFOAM, random access lists does its own iterator support. The linked lists have the iterator support in a subclass that is called iterator, basically. But I do recommend, if you are doing this level of writing code, that you just stick with STD things. So from things from the standard library, which will make just your life much easier down the line of your software development, basically. And another like a little bit more important one is the strategy pattern, which basically hides the implementation of your algorithms behind, let's say, a compatible interface. So if even if it's not really like inheritance based, if you still have like very similar kind of interface, well, you have like some functions that always return void and update, do something like this. Like we said, we see at the first of the talk, there's like x plus 1. So as long as there is like an operator plus, things can be generically generated for you without you actually needing that specific type here. And in OpenFOAM, a very prominent example here is just the divergent scheme class, which is composed of the interpolation scheme. The interpolation scheme is kind of used everywhere else. It's an interpolation scheme, everything uses an interpolation. But the div scheme here has an FVC divergence field, so to compute like the divergence field explicitly, and all it does, well, in the sense of Gaussian, divergence computation, is just to surface integrate whatever that dot a product is, well, with the normals and the field values, and then interpolate them. Well, these are from the faces, interpolate them to the faces. So VF here is like a volume field. It's at centers, cell centers. So you need the interpolation to the faces there. And that's how there is a because now you can use any kind of interpolation scheme for different things. So it's not just that interpolation schemes are compatible. No, it's div scheme uses interpolation schemes. Laplacian schemes uses exactly the same interpolation schemes. Whatever you compute with gradients and whatnot, you will always use kind of the same interface to the algorithms. We have two more, but the observer design here, this one I always find myself like adopting it without being like fully aware of that situation here. But in OpenFOAM, we have this nice object registry. So assume you have just changed the mesh. So assume maybe you added cells, you removed cells, or even you did some mesh motion. Right. And then suddenly you will have to remap all your fields, maybe update your boundary conditions, do all that, after work. So what you need then is, and it probably is not possible to just go in a for loop like for every single object that you have in memory to just update. And then, if someone else writes another thing, their own thing, it needs to be also updated automatically without them taking into consideration this type of things. So what OpenFOAM provides is an object registry that is attached to the mesh, for example, and everything that is relying on the mesh will register to that database, basically, right? And once the mesh gets updated, you get in that update function at the end, you just loop through the registered objects and update them. Well, but this again relies on them having this update mesh kind of function here, which is a very common way to update mesh objects, basically following a mesh update. And this is what the map is for there. So it's just to describe how the mesh has been changed, basically. So basically, these are things. So, for example, if you are doing like finite area on whatever patch on your mesh, you will need to update it with the mesh too. So it's not just fields and whatnot, right? So there are external things that need to match your mesh updates too. So they work in the exact same way. It's just you forward that map that describes the changes to the update mesh function, and everything just gets updated nicely automatically. So it's basically it's kind of an event system management. So it's like oh, I did update the mesh, so everything else needs to follow that. And the last kind of design pattern we want to take a look here is the visitor one, which is kind of pretty hidden most of the time, where you still want to separate your kind of data objects more or less, than your algorithms. So in this case, if you have like a finite volume matrix, which in OpenFOAM uses LDU addressing, so just extends LDU matrix, and the LDU matrix has a preconditioner, smoother, and the solver in there. And all of these types here are kind of very similar in what they do algorithmically. So what we want to do is have a separate entity that solves the equation and visits, but that entity visits the matrices basically, right? Well, it is not the entity that visits, it's just the matrices call that entity at some point. We just assume that is visiting it. It's not really a great example of the pattern, but I guess it's the closest I could quickly find. So these are basically all the design patterns I wanted to mention. To be honest, there are like a little bit more things I wanted to mention, but it's kind of 1 hour over. So I don't know. What do you say, Gregor? Do we continue? I can do like maybe 15 minutes more. Gregor, what's going on here?
Sorry, yeah,
Okay.
I was just muted.
Cool.
Yeah, I guess people have to jump to other meetings soonish, and also
Yeah, I guess. Let me maybe then 1 second. I wanted to just share the slides, because there are a little bit more things.
I mean, if you can, if you send me the slides, I can put them online and also the talk. So
yeah, they are already maybe online. I just need to find the link for my GitHub repository, and I will then be, yeah. But it's a little bit unfortunate, but the fun part is still coming, I guess. It's just the next section will go through a little bit for talking about the runtime selection table and how the object registry works. But I guess it's very easy to grasp. Everybody can just read through.
I will make a part 2 at some point. That would be also possible.
Yeah, I guess if you want to.
So first of all, I would ask if there are any questions from the audience. And if that's not the case, I would. I have some maybe quick ones. So first of all, about like functional programming. I mean, I had a look into Haskell, and you have to adapt yourself to a lot of recursions and at a completely different style. But after a while, if you get the hang of it, it's quite nice. But then the question would be, is there like any studies on performance for when using, for example, Haskell for linear algebra?
Yeah, I guess performance-wise, it's not like that far off from C++. C++ is just fast. It cannot beat it very easily, but it's not like Python grade, It's still quite like efficient. The main problem is, you don't have much libraries to begin with. That's the main thing, and you will like very, very quickly just get into a wall. For example, you cannot use like anything like MPI or like something like that. So it would be very, very hard to do like distributed programming there. At least to my knowledge, there is no such.
So there is one advantage, at least that I can think of for performance, because functions have no side effects. You can parallelize that with tasks, for example, very easily. It's somewhat natural, let's say.
Yeah, also, at least for Haskell, what I really like is, I think it's called Hugel. And what you do there is that they have a great type system. So you just say, I need a function which takes this and that of a type and returns something else. And then you can look in a online database for like all kinds of functions which do exactly what you want, and then just retrieve it. So in that sense, it's very powerful because you do a lot of like really abstract functions or modifications of whatever you need. And yeah, that's something I really like. And maybe one more comment or question about the least astonishment. I mean, when you showed the slide, I directly remembered, yeah, there's something in OpenFOAM with max. And I wanted to say, like, yeah, doesn't like one max do something like min or not? And it's exactly this. So I wonder whether this comes from the fact that OpenFOAM has been developed like more, not really in an open source sense, but like by a smaller group of people who are just like open sourcing their code. And what is like astonishing for some people is totally clear for others. And if you are working in like a small group of people, probably like the behavior of your code is pretty clear. But once you put it in the open, then people start saying, well, that is somewhat confusing what you implemented.
Yeah, I guess you're right in the sense that, like, I know some people who come from Lisp, which they see everything like as normal because they are like used to suffering, I guess. But once you get new people in, like you said, like people are kind of Python-y, or maybe like these like very new languages, Golang or something like that, which are not like they are not used to this kind of stuff. Even like I said, myself, it's like .max is not intuitive for some reason.
Yeah. All right. So do we have any further questions? If that is not the case, I really there's some by Bevan, or is it just a comment?
Somebody says the link to Tomislav's course is not right, but I think it was right. Maybe they had like a link opens correctly. Cool.
Great talk, Bevan. I can't speak. Just a quick question regarding not favoring free functions due to IDE issues. Is there not an advantage, however, in terms of no side effects and no dependency on state, which means all input must be passed into the function, which also states dependencies?
Yeah, that I agree that it would be very hard to imagine like a full kind of CFD software like taking like a pure functional like approach, which is I mean F# does like web stuff a lot, right? So it's .NET, so they have parsing all over the place, right? But still, like serialization and deserialization are like a separate like issue. But still, it's very, very hard to imagine like a CFD software, like a full CFD software package that has no state. It would be very hard because you will need to store something at some point.
Yeah.
You're doing matrices, so the thing is, there was like free functions. Yeah, the free functions are themselves are fine, like from technical point of view, but it's their discovery is quite hard. You will need like 6 months of training to just know that there is a Gmax.
Yeah.
Where do you see that Gmax? It's very like in respect to just writing p dot something, and the IDE gets you all the things. The IDE cannot like write all of the free functions for you.
I mean, I guess that is where I think it's called unified function call syntax or something like that in some upcoming C++ standard, where you would basically be able to call free function as you would do it with a member function. So you would only implement a free function, and then somehow magically your compiler understands that it works on just an object and turns it to a member function, or the other way around.
That would be cool, I guess. Yeah. It's just about the free functions are, like you said, technically they're fine. You can write like free functions. It's not an issue, but it's just the how to discover them is a pain. And most likely you will not include all the headers into your IDE, like auto completion system. That will requires 8 gigs of RAM for no reason. So yeah, it's just they are trickier to use, I guess. But I think I'm not really familiar with C++ modules. So right now, if they implement modules, I guess maybe discoverability for free functions it can be improved, I guess.
Okay, thanks. I've stopped the recording here, and yeah, thank you very much for your presentation. I think that is a great kickoff. And let me just stop the recording. Where is the? Yeah.